Hello everyone, welcome to Mayur Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is find the minimum and maximum number of nodes between critical points. So according to the problem statement, you will be given a linked list, and a critical point in that linked list is either a local maxima or a local minima. Okay, so a node is a local maxima if the current node has value strictly greater than the previous node and the next node. Okay, so for example, if you consider this one, which should we consider? I think we can consider this one. Okay, so let's take it to the board to understand it further. So as you can see, t is less than both of his neighbors. Okay, and so it was a local minima. Okay, and as you can see, 5 was greater than both of its neighbors, so it was a local maxima. Okay, so now these are local maximas and minimas, and what we have to do is from all the possible local minimas and maximas. So it is again mentioned that a local minima is strictly greater than its previous and next node, and there is a node that is mentioned in the problem statement. According to this, the local minima and maxima exist only if a node have a previous node and a next node. Okay, so given a linked list head, you have to return an array of length 2 containing the maximum and minimum difference between any two critical points. Okay, and critical points are those points at which we either have a local maxima or we have a local minima as mentioned in the problem statement. So a critical point is a point which is defined as either having local maxima or local minima. Okay, so difference, maximum and minimum difference between two critical points we have to return, and if there are fewer than two critical points, then you have to return -1 colon minus 1. Okay, so in that case you will be saying that okay, we are having basically less than two critical points, so we cannot compare anything, so that's why we are returning -1 and -1. Okay, so let's have a look at the constraints also before thinking of an approach. So according to the constraints, the number of nodes in a list is of range 2 into 2 to 10 raised to power 4, or order of 10 raised to power 5, sorry, you can say, and the node values are of order 10 raised to power 5. Okay, so these are the constraints. So let's think of an approach. So basically what we will be doing is we will be using a linear traversal here, and to make you understand how we will be using this linear traversal, I would like to bring the code also here so that it will take me less time and it will be convenient for me to explain you the logic. So let's bring the code also. So let's place this list here and bring the code. So let's zoom out a little bit so that we can copy the code. So this is the code. Yeah, let's paste it down here. As you can see, we have pasted the code. So this is our code. and this is our list. Okay, so let's discuss what's happening inside this code. I think this list should be pasted after this code is being pasted so that it can overlap. I think that it will not overlap. So anyways, it's good. We can anyways draw it if we want. So it's just for our reference. So what we are doing here is we are doing a linear traversal of this list. So let's mark the list, draw the list here again for the sake of clarity. 5 3 2 5 3 1, then it's 2, then it's 5, and then 1 and 2. Okay, so this is our linked list that is given to us. So what we are doing here is we were asked that we should be returning the minimum and the maximum distance. Okay, so minimum distance and the maximum distance we should be returning. So in order to return this distance, we have initialized these variables and we have taken values such that they will not be in range of minimum and maximum distance. For minimum distance, we have initialized to maximum value of an integer value in basically the implementation is in Java. So maximum integer value possible. And for the maximum distance, we have taken the minimum integer value possible. Okay, as you can see here. And then what we have done, we have taken one node and we are calling it previous node. So it will tell us or give us a reference to the previous node so that we can compare it with the current node. Initially it is set to our head, which is our first node in the list. So here 5 is our head. Okay, so this is our head and previous is here initially. Okay, so now moving back to the code, then we have initialized couple of variables. The first one is the location variable, which will be telling us the location at which we are at, and then minimum critical location. So the minimum location or the leftmost location at which you have seen a critical point till your journey at up till the current location. Okay, and maximum critical location is the maximum location at which you have seen a critical point up till your before your you can say uh, current location. Okay, so we would like to have these two variables, and then what we will be doing is we will be doing a linear traversal of the list. Initially we will be initializing a variable which will be our current node. Okay, so this is our current node. So this current node variable or the reference that it is holding will keep traversing the list in this fashion. Okay, so it will visit each node once and it will be doing so. And so this is what is happening here. Let me change color here. So okay, this is a linear traversal and we are doing so till we are reaching the end of the list. So I have written all the logics for check of whether we have end are at the end of the list, and how the node will be proceeding further in just one line in a for loop. Okay, I hope you are able to understand it. Then we will see our locations will be starting at 1. So this will be our first location, second location, third location, fourth, fifth, sixth and seventh. Okay, so these are our locations. Okay, so these are nothing but our locations. So we will increment our current location first in order to indicate very first location. Okay, and if you are not at the very first location, it means you are at least having a previous node. Okay, so this guarantees that you are having a previous node, and this line guarantees then a very next line current node is not equal to null, current node next. So it means that you are having at least one node ahead of the current node. Okay, so you this node is a viable candidate or a suitable candidate for local maxima or local minima. Okay, so then you will be checking whether the current node can be a local maxima or not. So this is the condition for local maxima. Okay, in the condition for local maxima, you are just checking that the value of the current node should be greater than both of its neighbors, the previous node and the next node. And this one is the condition for local minima. So you know, the node can be either a local minima or a local maxima. A local maxima or local minima. This one is for minima. Okay, and then you will see that your what is your minimum distance. Okay, so for getting minimum distance, you would be wanting to find the leftmost uh, or the rightmost maxima which you have seen before the current critical point. Okay, so rightmost critical point you will be wanting, rightmost critical point for getting your minimum distance. Because if you are able, let's say the rightmost critical distance was hypothetically this one, so you want is it to be closer than to the current critical point. So this is the current critical point. It can either be a local minima or local maxima, and this was your rightmost critical point. Okay, so that's why you will be wanting it to as much as close to the current critical point. That's why we are taking the difference between the current location and the maximum critical point. Okay, so this will give us the minimum distance. In order to get the maximum distance, you would be wanting to find out the difference between the current location, okay, and the minimum critical point, which is the leftmost critical point. Okay, leftmost critical point. Why we are doing so? Because if let's say this is our current critical point, okay, we want that the previous critical point should be as much as far towards left. Okay, so in order to get, so we will get the leftmost critical point. So that's why it will give us the maximum distance. So the maximum distance value will be updated here. Okay, and there is a condition for which we will update the minimum and maximum distance between critical points. The condition is that there should exist at least one critical point. Okay, so at least one critical point. So if the value of minimum critical point is changed, it means that there is existing at least one critical point. Okay, so then what you will be doing, if it is the very first updation of the minimum critical point or minimum critical location, okay, then you will be doing that updation. Otherwise you will be skipping that, because we want it to be the leftmost value. Okay, we will not be updating it every now and then. We will be updating it only once, when you have seen a critical point for the very first time in your traversal of this list. Okay, and for the max critical location or the max, we will be updating it every time we are seeing a critical point, because we want it to be as closer as to the current critical point. Okay, these are two things that you have again to keep in mind. And then obviously you would be wanting to have your previous node, because it will help you in comparisons. So you will update your previous node's value every time, irrespective of the fact whether you are at a local maxima or a local minima or a general point. Okay, So this is the whole logic. Once you are done with this linear traversal and all these checks, you will be having at your hand the minimum distance and the maximum distance. Firstly, you will check whether we have actually found a minimum or maximum distance. If it is the case, then you will be returning the values of minimum and maximum distance in a array. Otherwise, you will be returning -1 and -1. Okay, so this is the whole logic. Now let's talk about the time complexities of these ones. So let's take a fresh slide. Time complexity wise, it will be order of n, where n is the number of nodes. Okay, and space complexity wise, as you must have observed, we are not using any extra space here. We are just using a couple of variables, okay, or some one or two references, but they are pretty much constant. They do not depend on the size of the given list. So space complexity wise, it's constant. So constant extra space. So these are the complexities. If you are still having any doubts or any queries in general regarding this problem or its solution or anything, then you may ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Till then, keep practicing more problems, and I will see you in the next video. Thank you for watching.